Maybe someone will arrive or join. Nope. We have one viewer online. Appeared and disappeared. One person online connects, disconnects, connects, disconnects. Or maybe they are different. Oh, two connected. Okay, let's start. So, what I got for today, input circuits. Our previous lecture was disrupted. So, what we talked about, how to get analog signal or current into our digital processing space. The first idea can be current transformer. Ground. In theory, it's a transformer ratio multiplied by primary current. I search myself. Here is it's typical style of the 90s rack of the this was fault located. A digital, how to say it may be second generation of digital devices. This is base rack. Inside should be boards with all kind of electronics, but we are interested in this part. This is current input. So we have set 1, 2, 3 here current transformers. Typical current transformer. You can see quite huge primary wire with few winding 2 or 10. I can't remember. Thin secondary, and here they are. This can you see? Oh, no you can. This small red, these are load resistors. Current transformers should be load. Here, you see. Not time, medium size, set of 3 current transformers. What's good in this schematic? It's very robust. It can withstand huge overloads. It's thermally resistant. Disadvantage. Steel core of transformer introduce non-linearity. Actually, if we see transformer error, the system error as a function of current, it will be something like this, because of non-linearity of steel core. At the beginning, here at the beginning, also increase at small fluxes, we also will see increased error. Such kind of system, it's good for protection. In case of metering, questionable, and all, how to say, all light is on precision. What grade of precision do you need? How precise should be your device? I can sell this device, carcass of it in my possession. Other devices often use calibration. To correct error of current transformer, often calibration is used. What does this mean? In simple case, test signal, approximate double of ratio, for this that was double of ratio, is sent, error calculated, and correction factor is stored within device memory. What does this mean? We increase precision, but input cassettes, in our case racks, are not interchangeable. Devices are not interchangeable. You cannot use any part of input, this current input part, in another device, or you need to recalibrate. It may be a problem in mass production. For high-end purposes, something like 3-point correction chart can be used. A1, A2. It's a correction chart, linear approximation of error characteristic of your current transformer. When high precision is required, calibration should be done in 3 points, and correction or de-erroring characteristic should be put inside. To increase linearity, if we have problem with linearity and we have problem with dynamic range, some use here example. Here example. Magnetic system with air gap. This one adjustable. See, air gap in magnetic system. Air gap on magnetic gaps decrease load capability and increase linearity. It's done for sake of linearity. One moment. When we speak on traditional current transformer, they are not working well if input current contains DC component or aperiodic component of transients. Air gaps boost or increase performance for case of aperiodic, when we, for example, protection of power generator. When doing transients or transformers, when doing transients, high presence of a periodic component is expected. Air gap may help. Air gap increases performance, diminish error in case we have a periodic component. A problem with air gap, they are air gap transformers require higher culture of manufacturing because air gap should be precise. This one is not a good example. That's another problem with air gaps. If you will see leakage flux around this air gap. If you put them in rack, they start to influence one another, so-called crosstalk. To avoid crosstalks, can be done. Some can be done with geometry, placing transformers in 80 degree. But this design with open air gap isn't the best. Something can sometimes small. I saw them in reality very high level of manufacturing. In approximately in size of this capacitor. Small current transformers with air gap. They were placed, I would say, in steel, magnetic screen enclosure. Good practice for air gap transformer is usage of closed magnetic frame. Here, sigma is an air gap, closed frame. Outer legs perform magnetic screening from it prevent crosstalk. It's impossible to see this design. They have inner air gap. Magnetic systems like this, it's old, I can say it's an obsolete technology because they are linear. Such system with air gap, they used for interesting trick. Core. This air gap. One winding is for voltage. Second winding for current. Secondary. The secondary voltage is K1R pulse. It's performed linear sum. This type of system, it was quite popular in 70s in analog devices. Early digital devices used such system with air gap to perform multiplication even before digital processing. It was done to decrease computation burden on central processor. For early generation of digital processing, to decrease computation burden, some mass operations were performed in analog form with the help, they're called transreactors, with the help of linearized transformers. Nowadays, it should be considered obsolete, but if you need to recommission old device, be careful, you may find this object. And what should be pointed? Such input circuit put a quite high load burden on primary current transformer. They, while ordinary input circuit with transformer it consumes up to 2 volt amps. 2 volt amp is capped. Usually around 1 volt amp is a load from this circuit on primary. Such thing can easily put 10 times higher load. I knew cases when protection system failed, when such device was connected because of primary current transformer overload. It's not a thing you can ignore. Okay. I forgot to talk Rogowski coil. Another way to get current signal is so-called Rogowski coil. Current coil like this. Rogowski coil don't have a core, don't have magnetic coil. Rogowski coil needs only coil for mechanical strength. And there is one moment. Rogowski coil is very linear, but Rogowski coil has near zero load capability. It can be load. And Rogowski coil produces first derivative of signal. You need an integrating somewhere inside your processing chain or your processing train should be an integrating part to get current, because it produces derivative, not current, not something proportional to current, but something proportional to current derivative. Output is derivative. Rogowski coils are loved by all kind of portable instrument manufacturers. As an input, not a very popular thing. Rogowski coil lies on the shelf in the near room, but room owner disappeared. Okay, what can be done more? One more trick. What can be done when we need current is a usage of Hall sensors. This thing called Hall effect. If you take, say, block of, for example, germanium, apply E0 on one side, here will be your output, and put it in magnetic field. Result output will be a zero. Output will be proportional to magnetic field. Very often Hall sensors are used in automotive industry to sense ignition point, but also Hall sensors are used in measurement. Take magnetic coil like this. Put zero source, a zero source, and you will get, in theory, key E0 current as function of time. Looks very nice, including one important thing. Hall sensors can operate in DC mode. When you need DC measurement, Hall sensor can be your choice. They operate starting from zero. Such design looks nice. In reality, it's worth nothing, it's garbage. Why? Two problems. First problem, non-linearity. When you start to fighting for real dynamic range, you find that error is growing drastically. It's good for measurement current in tiny range. When we need real dynamic range, everything ends. Such design fails because Hall sensor has quite limited range of precise operation. And second problem, zero drift. Point of zero drifts mostly under the influence of outer temperature. This is garbage, works nothing. Good design of Hall sensor looks differently. Hall sensor of good design is something like usually they use toroids. This also will work. Magnetic core. Here will be our current. Here, place for Hall sensor. And additional winding powered from amplifier. This amplifier regulates it's set in opposite direction. It compensates with, so we have, say, flux 1, red, flux tube. This is amplifier produces signal and while whole EMF is not zero. Zero adjust circuit. So it's compensating scheme. Output goes here, this. Inverting. This one has a ratio -1. Inverting. Compensating scheme. Here in my hand. This is core. Here, this tiny is a sensor itself. It goes into the slot and operation amplifier and boost stage compensating amplifier. This one is for zero adjust. Much better performance, because Hall sensors always operate at zero. It's used to detect zero flux. It always operates near 0 point. So non-linearity of Hall sensors has no effect here. Anyway, needs periodic recheck for zero. For AC circuits, it's not a usually it's not a problem. For DC measurements, it can be problem. So Hall sensors need to be rechecked. One more very unusual and rare thing is a DC transformer, DC current transformer. It's something that sounds impossible. DC do not transform. What is DC current transformer? Rare thing. Problem when you need to measure very high DC currents. It's excitement circuit of large generator. You may face problem. High voltage, 600-800 volts, 1000 volts higher, and very high current, 2000 amps, 3000 amps. Sometimes it's a rare thing, but to measure such currents, what is used? DC transformer. Idea: take a steel core, primary winding, core. For example, you can drill holes, or simple. Here's my small transformer. Oh. Like it is done here. You see, it's current transformer, primary side, good thin wire, thick wire, secondary side, thin wire, and look what they done with core. You see, only half of steel in this closing part. Between legs, only half of the sheet. It's a transformer with saturation. We use effect of saturation. How this works? Primary side, secondary. This is powered from AC source. Without current, it's linear. In small currents, we operate somewhere here. So output is proportional to this excitement voltage applied. With higher current, working points shifts into saturation. And output decreases. This decrease with special crafted core, we can have, it will never be linear, but we can have decrease, not increase, but decrease in proportion as function of input DC current. This is DC. Inside, you will need to perform digital. It's a strange thing. Here, output is not increases when current increases, but in opposite, decreases. So you have to signal, and their ratio should be in negative. It's your DC current. It's the way to measure extremely high DC currents. Not precise, but it's a rare trick, but it can be, sometimes it's used. Okay, now most popular, use shunt resistor. Where is my I like this thing. 1.5 kilo ohms. This one for 1,000 amps. Here falls 1,500 amps, and here voltage will be 75 millivolts. Very nice, but there is one capital problem. Such design do not provide insulation. All our circuits will be hot. What to do? Where to run? Take a look on this unlucky metal. It's burned. What do we see here? Here they are. 1, 2, 3. This resistor shunts, one burned. And you see nice splits on the opposite sides, capacitors, and 1, 2, 3 resistors. Idea processing on a hot island. Idea of the hot island. BTV 1, 2, 3 quartz resonators. And here 1, 2, 3. What's this? Optocouples. Idea of processing on a hot island is we have so-called hot area. Some processing is done here and here, and this design what's done. Information processing result is sent via optocouple as a set of pulses. These islands each perform what? Voltage. They have voltage dividers. This is ground potential, hot to a DC. They process current. All this power. See this capacitor? It's a lot to obtain power. Each island, here we have 3 islands, has its own power and own voltage signal, own current under its potential. All these 3 blocks are hot. Only what methods do? Calculate energy. So results are sent by some kind of communication protocol via optocouples. Idea of hot island. Here we have very simple function. So simple communication can work, and processing on island is quite simple. On higher rate device, here all mass. Okay, I'm wrong. Not all mass, but initial signal processing, initial DSP, basic DSP function multiplication is performed on island. For high rank devices, this means what we need to replicate all our high performance structure on each channel's island and ensure insulation of islands between them and islands from frame. It may be extremely expensive. For high-rank device, processing on islands can be extremely expensive. Some do trick. We can only transfer signal. If we deal with low data flow, with low sampling rates, we can do what? We can have our current process. This one is hot. Insulation barrier, what color can be sent? Three very typical to auto industry, aviation industry. When analog signal, for example airflow, is converted into pulse frequency. This is converter voltage frequency. Pulse frequency is function of voltage. And pulses hot, ground potential. Pulses, for example, with simple optocouple, insulation barrier. So signal is converted into magnitude is encoded as a frequency and go through optocouple. Sometimes it works, it's, how to say, budget decision, but problem resolution. It's limit precision also, such kind of things. They are limited in time response. Another solution, higher end devices introduce another solution. Insulation amplifiers. This is hot area. In hot area, initial amplification, high frequency transformer. Here, initial amplification. M is a modulator. High frequency transformer. Signal is converted into, for example, frequency modulator. Demodulation, real signal. And also operation power. Signal, operation power. So transfer at this is hot barrier is done with the help of modulation. The modulation, simple amplifier, you get your signal. On the market are available insulation operational amplifiers. Appears like operation amplifier, like op-amp, only approximately this size. Inside, two transformer, modulation, demodulation, PWM switch. Here, only initial analog stage is performed on hot island, and then signals in analog form goes through what's interesting, such system may have feedback channel. What kind of feedback? To act as an operation amplifier, you need feedback. So they have feedback as traditional operational amplifiers. With the feedback, where the dog is digging? Dynamic range. We need 60 decibels, dynamic range. To do so, this amplifier can be with switchable amplification radio. One of the tricks to ensure necessary dynamic range is what? Our system has a controlled gain. For example, 1, 1/8, 1/6, and 1/32. Initial measurement is done by 1/32. Or signal too low, 160. Or still low, 1/8. Okay, we do it. It's a range extension. Idea how can we ensure this size dynamic range with speed and range extension? Having somewhere in our analog part switchable amplifier, then DSP multiplies as needed. For example, we have 10 bits ADC and plus 3 bits achievable with switchable range. So this system with amplifier allows us to have pre-range circuit for currents. This gives us dynamic range. We can measure 1 to 1, 1 to 4, 1 to 8, 1 to 60 with the gain control. Okay, what else? Voltages. Usually there is, what can I say? It's much easier to deal with voltage when it's current. Current is more problematic. With voltages, basic ideas. Simple voltage transformer. Idea number 1. Idea number 2. Divider. It's a bad idea. Simple divider do not ensure insulation. Divider with insulating copper. This will work. Another. For example, we need to measure excitement voltage. Better in opposite. Yeah, I'm doing okay. Capacitor, spark plug, it's the discharge. Capacitor, discharge, symmetric divider insulation barrier insulating opal. Over voltage protection. This is done for symmetry. And capacitors are noise filters. In my life, I saw 8 such devices. Something like this. Okay, more. Voltage transformer. This schematic works for DC. Cells. Extreme rarity Hall sensors. Sometimes as an input for devices placed on overhead line, field sensors are used. You have something like coil and antenna. This will sense for E component of magnetic field. This will sense for H component. All devices have them in size like this. To Novotec, you can find ACs. One microchip with all this inside. They are sensing E and H component of fields. Located under such input circuit, devices located under wires at poles. They sense actually something close to zero sequence field, E and H component. Field sensors. Okay, what else? Auxiliary signals. Sometimes we need auxiliary signals. What kind of signals? One, pressure. Pressure for generator protection. Pressure, casing pressure for switch for air operated. Sufficient air pressure for SF6, sufficient pressure in switch vessel. All these pressure sensors are very basic. Get it. Oh. It's a diaphragm, a cell phone, and a limiting switch. They produce binary signal. Absolutely no problem with them. When we need reading, I don't know, I know cooling systems, real pressure and cooling system and sufficiency of flow. When you create an integrated device, sensor. Usually you have kind of pressurized vessel, diaphragm, loading spring, and key elements, two variations, or tensiometric resistor. Have you ever heard about tensiometric resistors? Stripes of special material, the resistance is function of stretching. If you stretch them, they change resistance. Sometimes they are sold as a gluable. You just attach it to the surface you need, and they will change resistance as surface bends. So, or here, tensiometric resistors, or look what's there. Inside is a coil resistor. Here, take a look. See? Winded resistor and then contacting arm. If when diaphragm moves, arm goes to, it can be adjusted. This arm shifts and changes resistance. This will produce, can be used to as potentiometer. You will get voltage proportional to pressure. Some use this manometric round tubes, also attached to resistance. Sometimes not reliable because doing this contact points first and what else? Vibration may disrupt the contact point. If you really need, what mean? Hydro generators, always vibration. One problem is to get pressure, flow can be differential pressure. Also, mechanical opening of guide valves. When you need feedback from system, when system operates, you need mechanical position of guide vanes. Getting it with kind of resistor kind sensor nearly impossible. They do not survive. Water and vibration, vibration and water. For rare case, array of optocarpus can be used. But one of the trick what can be done is usage of magnetic sensor mutual inductance, based on mutual inductance, or sending coil, receiving coil, kind of screen, disrupting flux. Not precise. Good idea, working idea. stator coils, sending coils, and angle of coil is changed very robust thing. Then you only need to convert actually voltage, output voltage is a cosine of angle. So if you need linearity inside your logic, you need to perform arc cosine. Such device works better. Okay, what's next? What to do with binary signals? We need to get logic. What can it be? Switch state, open, close. One more. Before binary signal, one more thing. Temperature. How can we get temperature? Two cases. One, motor protection, where we need winding temperature. What? And resistance. Resistance, there are elements which resistance is changing with the temperature. Plant them inside winding, actually motor manufacturer to high-end models already came with thermal sensors as resistors inside windings. You only need to read resistance and set thresholds. When you need precise measurement of temperature, pressure thermometers, they base sealed vessel with liquid, it's kind of spiritual element, and precise manometer. Reading heat, pressure increase, reading goes up. Reading element, special arch type resistance. What a tricky thing, functional sender. At first it's a potentiometer, but see the form. They did they pre-programmed function inside sender. Come to increase to decrease computation load. Function was pre-programmed inside. Okay, coming back to logic. We may need state signals, switch on, switch off, and commands. Do switch on, do switch off, do something. Why commands? See? On the one hand, we can do all operation via HMI. Just put nice buttons, do switch it on, switch it off, increase, decrease. For devices operated once in a life, it's okay. For devices operated regularly, using a screen, they will not survive. They will not survive personal, nice experience. Why you using never touch screens on wood processing equipment? High end of protection, screens intended to usage on the ship's deck. You know why? Show me screen with very deep scratches. What happens? Your guy, your industry guy came, he has a screwdriver here in his pocket. He takes screwdriver out and start pushing your touch screen. That's how touch screens are destroyed in industrial environment. So if your device is intended for daily usage, I don't know, for example, solar system monitoring panel, which people are touching every day, it should be very resistant. In industrial environment, often much better to do what? Hide the screen from idiots and give them button. Operate, not operate. Sometimes need adjustment. Put one industrial grade vandal-proof potentiometer. Increase, decrease on the front panel. And give, so personnel working with device every day should have ability switch it on, switch it off, increase, decrease. All tuning should be in hands of trained personnel, not ordinary servicemen. So if it needs to be switched on, switched off, put external buttons. Nice vandal-proof external buttons. Okay, what about binary signals? Maybe I can show. Wait a second. I will bring one tiny binary signal to make it clear. Can I do it? Okay. Come here. One tiny relay. Maybe another. This one is good. It has EMI protection circuit. This one. And one button. One. This also has noise suppression circuit. Yes, I'm too good. Okay. Let's get scope. I need a scope. I'm looking at range box and thinking, where is my range box? Two more bars. Oh, here we are. Very simple circuit. Okay. Battery, push button, coil of my relay, with noise suppressor. I have no suppressor here. And this is my signal. Look what happens. compress. Okay, come on. Time. Okay, scope, what's up? Ah. In this scale, everything looks fine. But you see what happens? This part. This is how contacts makes. No button, no relay, no sensors with contacts. Never makes 100%. It's a contact dribbling. One moment, I will switch. Okay, it's how real contact makes. I need another relay. Another problem. Do I have something for 24 volts? Has suppression, noise suppression circuit. I can switch to this one. But it also open and normally open. Here is make of small relay. You see all this noise? It's how small relays make. Noise. Here is problem. When you input, only input is a binary signal, in real life you will never get 100% 1 instantly. You will get 1 0 1 0 1 0 1. What does this mean? Your input circuit should have what? First, you need something like this. What? First one is a kind. What we need? We should be immune to short spikes. Because the spikes may be noise. It may be computation noise from something. What the heck? Wait one moment, guys. Here is noise suppression circuit. I need to evaluate result. This one without noise suppression. What's up? Why it's so quiet? Something wrong. Oh. What was it? It's for big high voltage. Oh. This is make. See how it makes? Noise of make. But that's not all. Wait one moment, I will connect to the coil. Coil, how can I connect to the coil? happens at the coil. When no suppression circuit is present. Two previous relays had AMI suppression, noise suppression circuit. This one is bad.